Look closely at the world around you. The solid wood of your desk, the warmth of the morning sun, the air filling your lungs. It all feels undeniably, fundamentally real. But what if your perception is the most elaborate illusion ever engineered? What if the universe is not made of atoms, molecules, or tangible matter, but instead of pure, calculating data? This is the simulation hypothesis, a theory that transcends the boundaries of science fiction, operating at the bleeding edge of quantum mechanics and digital physics. The first profound cracks in our physical reality appeared in the microscopic realm. Consider the infamous double-slit experiment, a cornerstone of quantum mechanics demonstrating the observer effect. When particles, like photons or electrons, are fired through two slits unobserved, they act as an interference wave, rippling through space and creating alternating bright and dark bands. But the moment a conscious observer or a measuring device watches the slits to see which path the particle takes, the wave function collapses. The particle acts like a solid, discrete bullet. In 1999, an experiment known as the delayed choice quantum eraser took this anomaly even further, demonstrating that measuring a particle in the present can seemingly rewrite its past state. In the language of computer science, this is identical to a technique known as lazy rendering. Video games only render the environment that a player is currently looking at to save computational processing power. Is the universe conserving its RAM, only rendering objective reality when we happen to be paying attention?
The idea that reality is built on computation is not a new internet age fad. It traces its lineage back to the analog era of the 1940s, when chalk dust and old paper were the tools of revelation. In 1948, Claude Shannon published his mathematical theory of communication, laying the absolute foundation for information theory. Without knowing it, Shannon had created the conceptual substrate for digital physics. 2 decades later, in 1969, computer pioneer Konrad Zuse published a book titled Calculating Space, proposing the radical idea that the entire universe is essentially a massive cellular automaton, the very first formal digital physics theory. But the true paradigm shift came in 1989, courtesy of John Archibald Wheeler, a poetic visionary, mentor to Richard Feynman, and one of the titans of 20th century physics. In his labyrinthine Princeton office, surrounded by stacked monographs and the scratch of chalk on slate, Wheeler famously introduced the it from bit doctrine. Wheeler argued that all physical entities, every particle, every force, every star, are fundamentally information theoretical in their origin. The universe is not a collection of objects, but a vast ocean of yes or no answers, a binary cascade of ones and zeros. Matter is the byproduct of information processing. Wheeler systematically dismantled the concept of physical matter, transitioning his focus from orthodox general relativity into the radical belief that we inhabit a participatory universe, where the very act of existing and observing computes the cosmos into being. If the universe acts like a computer, we must inevitably confront the most unsettling question: who or what wrote the code? In 2003, Nick Bostrom, an Oxford philosopher, motivated by rigorous probabilistic deduction rather than theological dread, published a profoundly disruptive paper titled, "Are You Living in a Computer Simulation?" Bostrom stripped away the emotional baggage of existential dread, approaching reality as a solvable statistical matrix. He mathematically deduced that one of 3 propositions must be absolute truth. First, that all human-like civilizations go extinct before reaching a technological maturity capable of running fast, realistic simulations. Second, that advanced civilizations have absolutely no interest in running ancestral simulations of their evolutionary past. Or third, that we are almost certainly living in a computer simulation right now. Bostrom's logic is terrifyingly elegant. If even a single post-human civilization uses a fraction of its vast computing power to run billions of simulated universes, the number of fake simulated realities would exponentially outnumber the one base reality. Statistically speaking, the odds that we happen to inhabit the one original biological universe are billions to 1. Critics argue this theory flirts with anthropocentric arrogance, projecting 21st century video game psychology onto infinitely advanced godlike beings. Furthermore, there is the falsifiability crisis. A perfect simulation would deliberately hide its own digital artifacts from its inhabitants, meaning the theory skirts the edges of being completely untestable. Yet despite the skepticism, modern physics keeps stumbling over the source code.
To prove we live inside a simulation, physicists are actively hunting for the boundaries of our cosmic hardware. If reality is a digital construct running on a vast processing engine, it cannot be truly infinite. It must possess a fundamental grid resolution and a maximum memory capacity. In 2012, researchers of the University of Washington, led by Silas Bean, suggested that a simulated universe would display observable digital artifacts. They looked out into the deep void of space and pointed to the Greisen-Zatsepin-Kuzmin limit. This limit is a theoretical cap on the energy of cosmic rays. If the universe is built on a lattice-based simulation grid, particles simply cannot travel endlessly without interacting with that discrete geometric framework. The GZK limit mirrors precisely how a digital pixel grid restricts the speed and trajectory of simulated objects. Then there is the Bekenstein bound. This principle proves there is a hard, finite limit to the amount of information that can possibly be stored within a specific volume of space. If reality were an infinite continuous analog wave, it should be capable of holding infinite information. The fact that the universe has a strict mathematical cap strongly implies an underlying discrete digital structure. It is the finite RAM limit of reality itself. Deep inside facilities like the IBM Thomas J. Watson Research Center, cold, complex quantum chandeliers operating near absolute zero are primitive precursors to the ultimate computational machinery, a glimpse at the type of hardware that might run a universe.
The most shocking discovery and search for the simulation code came not from peering through a telescope, but from diving deep into the pure mathematics of string theory. In 2009, theoretical physicist Dr. Sylvester James Gates Jr. was analyzing supersymmetry equations, searching for the fundamental architecture of the cosmos. He was driven by the mathematical elegance of nature, but what he found was an astonishing structural anomaly that sent shockwaves through the physics community. Deep within the equations, Gates discovered complex geometric representations known as adinkras. These multicolored vertices and solid edges visually represent supersymmetry algebras. However, they are not just random geometric shapes. When Gates analyzed the exact mathematical structure of these adinkras, he realized they perfectly matched block linear error correcting codes. Specifically, they were the exact one-dimensional doubly even block codes, including the Hamming code invented by Claude Shannon in the 1940s to prevent signal degradation in early telegraph and computer transmissions. Why would the fundamental laws of nature contain the exact same error-correcting algorithms used in modern software engineering? Why does the universe need to error-correct its own existence as it calculates reality? For Gates, it was the profound shock of finding literal computer software buried in the mathematical fabric of string theory. It suggests that at the deepest levels, quarks, leptons, and bosons are not microscopic spheres of solid matter, but rather packets of self-correcting data, continuously executing lines of code to prevent the universe from crashing.
As we decode the universe, the very concepts of space and time are beginning to look like elaborate illusions. In 1997, physicist Juan Maldacena formulated the ADS-CFT correspondence, providing the mathematical backbone for the holographic principle. This mind-bending theory suggests that our entire three-dimensional reality is merely an emergent holographic projection emanating from a two-dimensional boundary of data. We are simply the 3D rendered projection of flat 2D information. More recently, in 2013, Nima Arkani Hamed and Yaroslav Trinka proposed the amplitridron, a multifaceted jewel-like geometric structure that radically simplifies the calculation of quantum scattering amplitudes. The most shocking aspect of the amplitridron is that it perfectly predicts particle interactions without any reliance on space or time. This breakthrough hints that space-time itself is not a fundamental reality, but rather a simulated byproduct, an interface created by our cosmic computer to help us process the data of reality. If space and time are not real, if matter is just a binary cascade, and if our physical laws are governed by error-correcting software, we are left with a staggering conclusion. We may not be biological beings floating on a rock in a dark, infinite void. We might be sentient lines of code, complex algorithms achieving self-awareness inside an unimaginably vast computing engine. And as we continue to unlock the simulation code, we must prepare ourselves for the ultimate question: what happens when the creators of our universe decide to turn off the machine?